गुरुर्ब्रह्मा गुरुर्विष्णु गुरुदेवो महेश्वरः गुरु साक्षात् परब्रह्मा तस्मै श्री गुरवे नमः.
Hey there, fantastic physics learners. So last time we talked all about spherical mirrors. Now we're going to zoom in and figure out how these curved surfaces actually create the images we see. Today, we're tackling two big things: how those images get formed and the really cool technique we use to map them out called ray diagrams. All right, let's get right into it.
You know, it all starts with something you've probably done a million times. You look into the back of a shiny spoon and your reflection is tiny and right side up. But then you flip it over to the scoop side and whoa, suddenly you might be looking at yourself upside down. Now that's not magic, not at all. It's pure physics. And today, we're going to break down exactly why that happens.
The whole answer to that spoon puzzle really comes down to understanding our two main characters in this story, the concave mirror and the convex mirror. You see, each one plays by a totally different set of rules when it comes to bouncing light around to form an image. And this really gets to the heart of their personalities. On one hand, you've got concave mirrors, the ones that curve inward, like the inside of a bowl. These are the total shapeshifters. Your reflection can get bigger, smaller, or even flip completely upside down, all depending on how close you are. Then you have the convex mirrors, the ones that bulge out. They're the constants. They give you the same predictable, consistent view every single time. Okay, let's really dig into the shapeshifter first, the concave mirror. This table here, it maps out a pretty fascinating journey. Just look at how the image changes as an object gets closer. When something's super far away, the image is just this tiny upside-down dot. But watch this. As the object moves from way out past the center of curvature, C, and gets closer, the image starts to grow, all while staying real and inverted. This predictable pattern is the absolute key to understanding how these mirrors work.
But here's where it gets interesting. There's this one special case where the concave mirror seems to just throw out its own rulebook. When you get really, really close to it, I mean closer than its focal point, everything flips. Literally. All of a sudden, the image pops up behind the mirror, it gets bigger, and it's right side up. This is the secret behind every makeup or shaving mirror. It's the one and only time a concave mirror will give you an upright image.
And then there's the convex mirror. As you can see, it's a much simpler story. Honestly, it doesn't matter where you put the object, the image is always going to be smaller, always upright, and always virtual, meaning it appears behind the mirror. This is exactly why they're perfect for the side view mirrors on your car. They give you a nice, wide, consistent view of the world behind you.
Okay, so we get what happens with these mirrors. But how can we actually predict the outcome without having the mirror right in front of us? Well, the answer is this beautifully simple and powerful tool that lets us actually map the path of light itself. It's a technique called ray diagrams. And what's so cool is that by drawing just a couple of specific beams of light, we can use geometry to figure out exactly where an image will show up, how big it's going to be, and whether it'll be right side up or inverted. It's kind of like having a blueprint for reflection. Now, to draw these diagrams accurately, all you need is a toolkit. And that toolkit is made up of 4 simple, unbreakable rules that tell us how light rays behave when they hit a spherical mirror. So let's get these down and you'll be able to predict anything. And here they are, our 4 golden rules. Each one describes the totally predictable path of a very specific light ray. Mastering these is like learning the basic moves in chess. And you want to know the best part? You only need to use 2 of them at a time to figure out exactly where the final image is going to land. All right, let's kick things off with rule number 1, the parallel ray. This is all about any ray of light that comes in towards the mirror, traveling perfectly parallel to that main center line, which we call the principal axis.
Now, for a concave mirror, when that parallel ray hits the curved surface, it gets bent inward. It's reflected so that it passes directly through one very important spot, the principal focus, which we label F. You can almost think of the concave mirror as a collector, gathering all those parallel rays of light and funneling them to that one point.
For a convex mirror, though, that same parallel ray does something totally different. It hits the surface and bounces outward, scattering or diverging away. But here's the trick. If you trace that reflected ray backward in a straight line, it looks like it came from the focal point that's behind the mirror. And that's why we say the focus for a convex mirror is virtual.
Next up, rule number 2, the focus ray. And as you can probably guess, this is pretty much the exact reverse of rule 1. This rule is about any ray of light that, on its way to the mirror, first passes right through the focal point. And just like you'd think, since it's the inverse of our first rule, any ray that goes through the focus before it hits the mirror will bounce off and travel away perfectly parallel to the principal axis. And this little trick works for both types of mirrors. See? Physics loves symmetry. Okay, on to rule number 3. And honestly, this might be the easiest one to remember. This ray is any ray of light that travels along a line that goes right through the center of curvature, C. That's the center of the giant imaginary sphere that the mirror was sliced from. The secret here is pure geometry. Because this ray is traveling along a radius of that original sphere, it hits the mirror's surface at a perfect 90-degree angle. And in optics, anytime a ray hits a surface head-on like that, it just reflects straight back along the exact same path it came from. It's a perfect U-turn.
And finally, we have rule number 4, the oblique ray. This rule covers any ray of light that happens to strike the mirror at its dead center, the point we call the pole, right where the principal axis touches the mirror.
At this one special spot, the curved mirror acts just like a simple flat mirror. The principal axis itself becomes the normal line, and the ray just bounces off at the exact same angle it came in at. The angle of incidence equals the angle of reflection. Simple as that. Okay, we've got our toolkit, we know the 4 golden rules, now for the fun part. Let's actually put them to work and see how we can use them to find any image formed by any spherical mirror.
And this right here is the key that unlocks the entire process. You do not need to draw all 4 rays. Just pick any 2 from our toolkit, whichever 2 seem easiest for the situation. Draw them out, reflect them using the rules we just learned, and then find the exact spot where those 2 reflected rays cross. That single intersection point, that's it. That's where the top of your image will be. It's really that elegant.
So let's just walk through an example. Imagine you have an object. First, from the very tip of it, draw a parallel ray and reflect it down through the focus. Got it? Okay. Second, draw another ray from that same tip, but this time send it through the focus and reflect it out parallel. And look, you see that spot where they cross? That intersection tells you everything. Exactly where the image is, how big it is, and the fact that it's upside down. It really is that simple.
You know, it's so important to remember that these diagrams, they aren't just little sketches. They are basically geometric proofs. They take what seems like the chaotic behavior of light and turn it into a science that's predictable, understandable, and gives us the power to map the journey of light itself. I mean, think about it. From the big security mirror in the corner of a store to the complex shape of a car's headlamp, this physics is absolutely everywhere. So, now that you know the rules of the game, where do you see them playing out in your world? Hey, if this explainer helped you see things just a little more clearly, do me a favor and hit that like button, share it with someone who might need it, and subscribe for more deep dives into the science that's all around us.